I once showed up to a dinner party so embarrassingly early that the host was like literally still in their bathrobe, vacuuming the living room.
Oh no, that is deeply uncomfortable for everyone involved.
It really is. It honestly felt like I had arrived before I even, left my house.
Well, mathematically speaking, you might have just been acting like a photon.
Right, and that is exactly what we're exploring today on Intellectually Curious, the deep dive dedicated to, learning and exploring the wondrous, optimistic frontiers of our universe.
Yeah, it's such a great topic today.
It really is. Our mission for this deep dive into the sources is looking at recent experiments led by Ephraim Steinberg, and they demonstrate that quantum particles can actually spend a negative amount of time inside a medium. So, let's just jump right in. How does a particle of light, a photon, spend less than 0 seconds inside a cloud of chilled rubidium atoms?
It completely defies our everyday logic. So the researchers fired single photon pulses. Those are like individual tiny packets of light.
Right, single packets.
Yeah. They fire them into a cloud of rubidium atoms. Now, these atoms are chilled to near absolute zero, which makes them highly receptive to interacting with the light.
Okay, that makes sense.
Usually, a photon gets absorbed, and the atom holds on to that energy for a brief moment. We call that an atomic excitation. And then, it spits the photon back out.
Right, so the photon enters, it pauses while the atom holds its energy, and then it leaves. That sequence obviously takes a positive amount of time, right?
Exactly. But a tiny fraction of these photons pass straight through the cloud without being scattered.
Wait, they just fly right through?
Yes, and when the researchers measured the arrival times of those specific photons, they found something completely impossible. The photons arrived earlier than if they had just traveled through an empty vacuum.
Wait, early arrival is one thing, but how does arriving early translate to spending negative time inside the atoms? If the photon passed straight through, didn't just bypass the atoms entirely?
So that is the brilliant paradox here. Even the photons that seemingly pass straight through, they still interact with the atoms.
But we run into a major physics hurdle trying to prove that interaction. It's called the quantum Zeno effect.
Right. I saw this in the sources. They compared it to the myth of Odysseus and Calypso.
Yes, exactly.
The idea is that, if the gods watch Calypso too closely, they freeze her actions and she can't get to Odysseus. So in quantum mechanics, if you try to directly observe a particle while it's in a fragile state, you just freeze its evolution.
Spot on. Measuring the photon directly destroys the very interaction you are trying to study. You cannot just put a stopwatch on the photon itself.
So this is where that Josiah Sinclair analogy comes in, right? It's like trying to calculate how much time a specific fleet of cars spends driving through the Lincoln Tunnel.
Right.
But if setting up traffic cameras inside the tunnel magically vaporized the cars, you'd have to find another way. So instead, you measure the carbon monoxide left behind.
Which is such a brilliant workaround.
Yeah, because cars emit exhaust at a steady rate. So the total amount of gas tells you exactly how long they were inside without you ever actually looking at the cars themselves. That is a phenomenal way to picture it. In this experiment, the carbon monoxide is the energy left behind in the rubidium atoms. The researchers used what's called a weak measurement.
A weak measurement.
Yeah, instead of a harsh, direct observation of the photon, they gently probed the rubidium atoms with a completely separate, low-intensity laser beam just to measure their excitation levels.
Oh, wow. But tracking millions of experimental data points like that sounds basically impossible without great tech, right?
Yeah.
Which actually brings me to something I want to mention really quick.
Oh, yeah.
Yeah, this podcast is sponsored by Embersilk. If you need help with AI training or automation or integration or software development, they are the ones to go to.
Absolutely.
If you're uncovering where agents could make the most impact for your business or personal life, check out embersilk.com for AI needs. Anyway, back to the photons. Does this gentle probing mean the data from a single run must be incredibly faint?
It is. A single run gives you almost no usable data. But by running the experiment millions of times and averaging the results, a crystal clear picture emerges.
And what did that picture show?
Well, the data showed that for those early arriving photons, the exhaust left behind.
The time spent as an atomic excitation.
Right. That time was mathematically negative.
Okay, my brain is melting a little bit here. A negative amount of exhaust. I have to ask the elephant in the room. Does this mean time is literally flowing backward? Are we looking at retrocausality where the effect happens before the cause?
I know it sounds like it, but not quite. Causality is completely safe, and we are not building time machines.
Okay, phew, good to know.
Yeah. We have to remember that a photon is not a solid, tiny marble. It is a wave of probabilities. We call this a probability amplitude.
A wave of probabilities, okay.
Right. And when that wave enters the atomic cloud, the atoms act almost like a filter. They reshape the wave, absorbing the trailing edge of it, which effectively pushes the peak of the wave forward.
Ah, so the wave's peak gets shoved out the other side sooner than expected, making it arrive early.
Yes. And because of how these complex quantum waves interfere with each other, the math governing the time spent in the excited state dips below zero.
Wow.
So it is not a clock running in reverse. It's a consequence of how quantum probability waves behave when they are reshaped by a medium.
That really highlights how wild the microscopic world is. It's just so counterintuitive.
It really does. And it is incredibly inspiring, honestly.
Yeah.
Humanity is still peeling back these fundamental layers of reality. The fact that we can now build experiments delicate enough to measure negative time is a deeply optimistic sign for the future of scientific discovery.
It makes you wonder, doesn't it? If our everyday, forward-ticking stopwatch view of time completely fails at the quantum level, what other basic features of reality are just waiting for you to beautifully reimagine them? It is a lot to think about.
It really is.
Well, if you enjoyed this podcast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.